Good day. In the beginning of 19th century, two boilers had been exploded in Massachusetts, which motivated the governors to demand for prompt action for improving public safety. Then, between 1909 and 1911, two states started drafting their own laws as an act relating to the operation and inspection of the boilers. I am Ahmed Ibrahim, and today I will talk to you about the codes and their requirements from piping stress analysis point of view. The piping codes has assembled a set of procedures and specifications covering the minimum requirement for materials, design, fabrication, erection, inspection, and testing. There is a great difference between the code and the standards. The code, as I had mentioned before, it gives the minimum requirement for the designers and the material inspection, the fabricators, even for the erection, to apply it on the piping systems, while the standards contain design and construction rules and requirements for individual piping components such as the elbows, the T's, and valves. The American Society of Mechanical Engineers, ASME, established a committee in 1911 to formulate rules for the construction of steam boilers and other pressure vessels. This committee is now known as the ASME Boiler and Pressure Vessel Committee, and it is responsible for the ASME Boiler and Pressure Vessels codes. Also, ASME has established other committees which develop many other codes and standards, such as the ASME P31 for the pressure piping. All these committees are following the procedures of the American National Standard Institute, the ANSE. Also, in 1954, the engineers who designed the first commercial nuclear reactors recognized a need for a set of design and fabrication rules to facilitate the development of safety, economical, and competitive nuclear reactors. As there were many similarities between thermal neutrons reaction and traditional steam-powered pressure vessel, the nuclear industry was relying on ASME Section 1 and Section 8 to help standardizing their practice. But in 1963, ASME published the first edition of the ASME Section 3, which was mainly concentrating on the nuclear vessels. Over the years, the scope of the ASME Section 3 has expanded to cover practically all of the pressure and liquid storage component involved in the nuclear power sites. Nowadays, nuclear power is further divided into three classes, while the P31 is presently divided into 7 sections for the pressure piping. This is a brief history and introduction for the codes and the American code, the ASME. For the non-nuclear piping codes, I had considered, or I had selected the main 3 piping codes that we are using, mainly using in our stress analysis. This piping codes is the P31.1 for the power piping, and P31.3 for the process piping, P31.4 for pipeline transmission for liquid hydrocarbons, and P31.8 for gas distribution, which is pipelines which consider which carry gas. P31.1 are used for the design of power plants, and since power plants is important facility which it could not P failed or shut down, the factor of safety of this code is considered high. If we are comparing, for example, with P31.3. While P31.3, from its name, it's used for the design of petrochemical. P31.1 and P31.3 nearly have the same design equation, except the difference comes with the allowable stress used in every code. We have also P31.4 for the cross-country petroleum pipelines run through mainly unpopulated area. Also, we have the P31.8 for gas transmission and distributing piping system, which divided the pipe into 4 location classes. Range from location class 1, where there is a few people, to location class 4, where building and traffic are heavy. I had bring small comparison between the ASME P31.1 and P31.3. This comparison based on the piping stress analysis point of view. You will find out that the factor of safety in the P31.1 is higher, which is 4, from the P31.3, which is 3. The lifetime for the P31.1 is 50 to 40 years, while the lifetime in the P31.3 facility is 30 to 20 years. If we are looking to the hydro test, you find the hydro test is the same. It's 1.5 design pressure and 1.2 design pressure for pneumatic testing. The allowable stress or allowable strength is the maximum stress that is allowed to be applied on the piping material, which equals the yield point stress divided by appropriate safety factor. This safety factor, why we consider it? We consider it because it counts the loads and the forces which may happen during the lifetime of the facility, the non-uniformity of the material, inaccuracy that may happen by the stress analysis engineer. The basic concepts here that the maximum stress of the pipe should always be smaller than the allowable stress of this material. When we apply loads to an object and keep increasing the magnitude of this load, at some point this material will fail. Okay, how can we know the fail, when this fail will be occurred? We typically find the following stress strain curve, from which we can deduce possible limits for the material stress. The first limit would be the yield strength, to make sure there is no plastic deformation from the pipe. The second limit would be the ultimate strength, to make sure that there is no rupture in the pipe. Actually, I found this on website called material.org, and it was very good to show that the tensile strength with different stages, on different stages, from starting of the test, when it reached to the yield point, when starting the plastic deformation at the ultimate strength, and when it reached to the fracture. And this is the tensile testing. We have two materials, the ductile and the brittle material. In the brittle material, we usually use the ultimate strength, while in the ductile material, we have the 2-point, the yield, and the ultimate strength. Okay, but it's easy to define for the uniaxial stress the normal stresses. and it can be easy to know when it will reach to the yield strength for the ductile material and the ultimate strength for the brittle material. But what happened, or what about more complex case of triaxial stress? How can we predict the failure? It's very difficult to predict the failure. Here comes the importance of the material failure theory. The failure theories simply it allows us to predict failure of the material by comparing the stress status in the object with material properties that are easy to be determined, like yield or ultimate strength of the material that we can obtain by performing uniaxial stress. The maximum stress theory, which is the ranking theory, maximum strain theory, the maximum shear theory, which is Tresca theory, maximum energy theory, maximum distortion energy theory, von Mises. Usually in the stress analysis, we have these three theories that we care about them: the maximum principal stress theory, which is the ranking theory, the maximum shear theory, which is Tresca theory, and the maximum distortion energy theory, which is the von Mises theory. We can use the yield surface for these three theories to compare between them. Ranking theory states that the material will fail if one of these stresses reach to the yield strength of the material. And if we try to plot it, it will come as a square connecting between the yield strength points of the material. Sorry if the square is not very clear, but I'm trying to do it with the mouse. And let's consider this a square, sorry, and this will show the range for the principal stress theory, which is the ranking theory. While if we are talking about the von Mises, the Tresca theory, the Tresca theory states that the yield occurs when the difference between the maximum and the minimum principal stress is equal to the yield strength of the material. If we try to plot it, you will find out that the range of the plot will be this blue line. And this is the representation in the yield surface for the Tresca theory. While if we try to plot that von Mises theory, you will find out that the equation will give you an elliptic equation that can be drawn with this ellipse. As you can see, the maximum principal theory, while it's easy, but it's not conservative theory, because all of this outer range. So when we make our studies, we depend on the Tresca and the von Mises theory. Both of them agree well with the experimental observations. Although von Mises agrees slightly better. But Tresca yield surface lies entirely inside the von Mises surface, meaning that Tresca is more conservative. And this is why the ASME is adopting the Tresca theory in his calculation, while the von Mises is usually adopted by the finite element analysis because it's dependent on energy, so it's easy to be shown in contours. Since we are talking about failure theories, we need to know first what are the loads that applied on the pipe, or the pipe will face it while it's under operation. First of all, let's consider a piece of pipe and check what loads it see in the operation. First of all, it will see the longitudinal stresses with the bending moments. Also, it will see the torsional load, which create a shear stress. And because of the internal pressure inside the pipe, it will see the hoop stress and radial stresses, which is considered from the outside and the inside pressure on the pipe. So let's see, we have the longitudinal stress, which is the force and the bending moment, and which is the force per cross-section area and the bending moment per the section modulus, and hoop stresses, which considered to be very low and negligible since we are studying the thermal strain inside the pipe. The radial stress will be equal to 0 because we are not studying any dead weights. We are studying the thermal stress that affect on the pipe. So we will consider it equal to 0. And the shear stress, which is the shear affecting divided by the section modulus. If we want to go deep in the maximum shear stress theory, since it is the one that it's adopted by the code and all the calculation is based on this theory, we need first to consider a free body diagram from the pipe, which I mean it's for the people who are need to refreshment. It's the control volume from the pipe, from the body of the pipe. It would be like this. This is the our control volume, and the forces that is applied on it is the longitudinal stress, the hoop stress, the shear stress, and the radial stress. Okay, let's simplify this by have a 2D section. A 2D section, if we look from this side, from the top side, we will see this view where we have the longitudinal stress, the shear stress. Of course, we have the hoop stress here, which is SH, but it's not shown since we are considering it a negligible load. Okay, if we try to cut this square and creating a new face or new surface, this surface will have a force and shear also, which try to make a balance with the other two forces, the other two stresses, which is the longitudinal stress and the shear, the hoop stress, which let's consider as SH, and so we will have SX and shear tau X. For example, it will, if we apply this, we will have this view where we have sigma X and tau Z. Also, these stresses are normal stresses perpendicular to the shear and perpendicular to the surface of the axis of the force. But this sigma X is rotated with angle. Let's consider it angle phi. How can we translate and get this forces? The most convenient tool that we have to do this transmission for the stresses on it on this new surface is Mohr's circle. Mohr's circle. First of all, what we will do, we will take the known points or the known data and we will apply it here. What we know the SL and the negative tau, which they are here. So we have the SL and negative tau, and we have the SH and positive tau. Of course, the we why we have this negative, because we are considering a clockwise study, so the shear is in the negative direction of this clockwise. Before somebody asks me why it is negative, we are considering a clockwise for the forces. This is why the shear is coming by negative. And why we have this on the shear axis? Because we consider SH equal to 0. And let's draw a circle that path between these 2 points, and considering the line between them is the diameter of the circle. And we have this. How can we know sigma x and sigma y? The rule with the Mohr circle that the angle phi will be 2 phi on Mohr circles. So we will measure here 2 phi, and we will have a line coming from here up to the edge of this circle and continue here. And this point will be sigma x and tau z, which they are this one. So this is how we can know the points on Mohr circle. On the other hand, we have here the S1, and S3, S2. S1 is considered to be the maximum principal stress. S3 is considered to be the minimum principal stress. S2 is of course, the shear stress. S2 is considered to be the shear stress, which have the 0 radial, and it's equal to 0. Not shear stress. It's equal to 0 since it's already on the axis of the shear. I'm sorry for this mistake. But after all, we are studying the maximum shear theory. How can we get the maximum shear theory from Mohr's circle? The maximum shear theory is the radius of this circle. Here, as you can see, this is the maximum shear theory. How can we know the length of this radius? Simply what we will do, that we will have, this is the diameter of the pipe. If we link this with a straight line and go upward, we will have a right angle triangle, which can apply, we can know this side of the right angle triangle by applying the Pythagoras theory. What is the length of this line? The length of this line will be 2 tau, since here from here to here is tau, and from here to here is equal to tau. And the length of this side is SL, here tau and tau. If we apply the Pythagoras theory, which states that this line will be equal to the square root of square SL and square 2 tau, and divided by 2 to have the radius, and we can get the shear stress, the maximum shear stress. And this is the equation that is used for the maximum shear theory. We done some modification on this equation based on the code requirements to be applied on the equation 17 in the code. This is the end of my presentation. Let me summarize what was inside this presentation. we was talking about the codes and we give a brief history about the code. And we are facing the main, we talked about the main four codes that we are using for piping stress analysis: the P31.1, the P31.3, the P31.4, and P31.8, which this four codes are commonly used for piping stress analysis. We make a brief comparison between the P31.1 and the P31.3, and we know that the factor of safety in the P31.1 is equal to 4, which is higher than the P31.3, which is equal to 3. And the lifetime in the P31.1 is 50 to 40 years, while the lifetime in the P31.3 is 30 to 20 years. Also, we talked about the failure theory, and we said that we have three failure theories that we used in for the ductile material: the maximum principle theory, the maximum shear theory, and the maximum distortion theory. And we said that the code is adopting the maximum shear theory, since it's more conservative. Also, we said that the maximum distortion energy theory is the one that mostly adopted by the finite element analysis, since it's dealing with energy and it can be represented in contours. And also, we talked about what are the loads that applied on the pipes. And we go deep in the shear stress theory, and we explain the Mohr circle and how we extract the equation of the maximum shear theory. I hope this presentation was helpful and the information inside it was useful for you. Please, if you like this presentation, give me a like and subscribe to my channel, and press on the notification bell for more videos. Thank you.